This is a wave of light and matter, bound together, moving with extraordinary precision across the surface of a crystal. In 2026, researchers led by Atrey Ghosh directly visualized this phenomenon in a hyperbolic material called molybdenum oxydichloride, or MoOCl2. They tracked a long-range anisotropic plasmon polaridon, an LRAP, propagating over 10 microns. But this discovery poses an immediate physical problem. This single natural van der Waals crystal supports both tightly confined short-range polaridons and these newly discovered highly mobile long-range modes at the exact same time. Standard nanophotonics cleanly resolves this tension. It labels the wave as a guided mode, its shape and speed determined by the material's dielectric properties and boundary conditions. The TCGS-SEQUENTION framework views this guided mode as a specific type of evidence, a shadow carrier. This reclassification suggests the wave represents a deeper interaction that only becomes visible through the crystal's unique geometry. Modern physics frequently struggles with a specific category error, taking a high-resolution, measured experimental output and assuming it reveals the source-level reality of the universe directly. The TCGS-SEQUENTION framework demands strict discipline here. We must separate the underlying electromagnetic material relation from the readable traces it leaves behind in the laboratory. Look at this projection structure. The MoOCl2 crystal does not manufacture the physical relation at the bottom. Instead, the material acts as a highly constrained environment, filtering that deeper relation until it casts a readable shadow onto our measurable plane. To interpret this MoOCl2 shadow accurately, we have to systematically deconstruct the three components that make it visible: the sharp physical edge of the crystal, its internal directional lattice, and the specific operational clock used to record the wave. Before we can redefine the foundational territory, we first have to master the strict boundaries of the orthodox experimental map. The framework enforces a rule called orthodox artifact discipline. We cannot make philosophical claims about a phenomenon until it is rigorously classified using standard physics. The timeline of light matter carriers begins with standard isotropic surface plasmons, ripples expanding uniformly. Then, tunable phonon polaritons in boron nitride showed crystalline geometries squeezing the wave's shape. Later, anisotropic interfaces forced these hybrid waves into highly specific directional pathways. When we arrive at the 2026 MoOCl2 experiment, the first requirement is ruling out standard optical artifacts. Specifically, the researchers had to prove they weren't just seeing lossy bulk volume ghost modes. The Ghosh data successfully passes this screen. It proves the mode is surface-sensitive, exhibits predictable dispersion, and sustains directional propagation well past normal loss limits. Because this shadow map is physically valid and artifact-free, the LRAP is now a legally admissible subject for ontological reclassification. This requires looking directly at the internal atomic reality of the MoOCl2 crystal, governed by its dielectric tensor. In standard nanophotonics, MoOCl2 is described as biaxial and highly anisotropic. Its electromagnetic response changes drastically depending on which structural axis the wave attempts to travel down. Under TCGS-SEQUENTION, we apply a specific term to this geometry. This anisotropy functions as an anisotropic projection corridor. This corridor acts as a rigorous physical filter. It actively rejects certain energy paths, selectively permitting wave propagation exclusively along the crystalline A-axis. But this filtering is conditional. When the incoming light shifts its angle off-axis, the propagation immediately stops. This resolves our initial paradox. A single material hosts both long-range and short-range modes, simply because different excitation parameters activate different internal corridors. Observing multiple distinct wave behaviors inside one crystal suggests we are simply viewing different admissible shadow traces of the exact same source relation. We must also move outward, from the internal atomic corridor to the physical termination point of the MoOCl2 flake, the edge. In orthodox material science, a crystal edge is treated passively, as the point where the physical volume of the substrate stops. TCGS-SEQUENTION reclassifies the edge as a highly active coupling interface, strictly required for the polariton to become readable in the first place. The edge mathematically compensates for the momentum mismatch between free space light and the confined wave, launching the guided polariton into the projection corridor. These wave packets then travel completely across the crystal and cleanly reflect off the opposite edges. The physical boundary serves as a necessary translation device, converting an invisible state into a coherent, measurable shadow trace. To understand how this trace is measured, we have to look at the specific protocol that captured these images: time-resolved photoemission electron microscopy, or TRPEM. The TRPEM system reconstructs dynamics by firing two interferometrically locked laser pulses. These pulses are separated by a scanning laboratory delay parameter known as delta T. This creates a dangerous ontological trap. A sequential spatio-temporal visualization easily invites the belief that we are watching a fundamental progression of the source-level universe. We have to enforce strict temporal type discipline. The delta T variable is an operational clock index used to order shadow registrations in the lab, rather than a map of true time. This distinction matters deeply when we examine the kinematic velocities mathematically extracted from these operational time slices. The experiment calculates a phase velocity of approximately 0.98 c. This metric describes the internal oscillatory pattern of the mode, rather than the forward movement of physical matter. There is also the group velocity, measured at 0.68 c. This metric represents the overall envelope transport of the wave packet. Phase velocity, group velocity, and overall propagation length describe different behaviors. They must remain rigidly decoupled as independent map-level descriptors. Conflating these separate velocities into a single claim about source-level transport ignores the distinction between the measured shadow and the underlying source. When we bring all these deconstructed elements together, we arrive at the formal TCGS-SEQUENTION carrier schema, translating the relation, through the corridor, into the trace. KLARAP represents the readable shadow carrier. We add external filters, edge geometry, polarization, and frequency. Next, internal material constraints, the dielectric tensor and flake thickness. Finally, we enclose these inside a projection operator applied to the underlying relation, all governed by the specific TRPEM readout. This schema proves the carrier's existence is highly conditional. Alter any physical boundary or measurement parameter, and the shadow output changes entirely, while leaving the deep source relation perfectly intact. We arrive at a clear hierarchy, where the dielectric tensor acts as a navigational corridor rather than the source of the physical relation. The long-range polariton observed in the lab serves as a legal carrier, a readable trace selected by the crystal's geometry. Likewise, the high-resolution TRPEM delay scan provides an operational index for measurement, ordering our observations without revealing the source's timeline. The MoOCl2 result replaces the idea of an unexplained anomaly with a disciplined instance of nanophotonic carrier cartography. Rigorous, disciplined shadow mapping allows us to observe incredibly complex light-matter dynamics without ever falling into the ultimate ontological trap, mistaking the measurable carrier for the profound underlying territory.